Okay, so I think if you go, so you have the workshop page, and you have class files here, and you click, there should be a folder called Convergent extension. You click there, and you can download the simulation. And basically what you see is this model here, simple 2D conversion extension, okay? And this particular model example that I did is I'm not doing XML, I have everything in Python. So instead of having 3 files, I have only 2. The main Python file, where you have see all the equivalent to XML code, and the Python file with all the steppables. Okay. In this case, I have actually 4 classes, 4 step. The first one is just to set the target volume of all the cells in your simulation. So start for all the cell list, set the target volume and set the lambda volume. Okay. And then I have 3 steppables. One simple 2D convergent extension steppable, intermediate convergent extension, and advanced convergent extension. Okay. The simple one, if you open here, is just what we had before. After some time to allow for the system to relax, I make 2 functions to delete the links and then to create new links. And delete links, I go over all the cells, get the list of all its links, and then delete them between the cell and the neighbor. So this FPPD here stands for focal point plasticity data. And then you can get information like the lambda string between that link. So is go over all the possible pairs. And here I'm saying that fp.neighbor address returns the cell that it makes the neighbor. And then I delete the link between the cell and this neighbor. Okay. So, and then after I do this, then I do the create links. And then I set the lambda to be 10, the maximum angle to be pi/4 or 45 degrees. And then I go over all cells, over all neighbors. If it's a neighbor, not a medium, I get x, y, z from this function, get the vector between the cells. And remember this invariant here means that it will give the shortest distance if you have boundary conditions in your simulation. Then calculate the angle. So here in this example, I did without the NumPy, with just the math import everything, but maybe it's a better idea to actually use NumPy for all these functions. And then I check the angle on both sides, and if it's within the range, I just make I just create the link. So I can run this, for example. So this is the simple 2D steppable. So it will return 3 elements and can store them as a list, like you did, as vac equals, which is the default. Or if you just write xyz equals, then you actually open that list and store each one in a different variable. But Python do that. So you can store either as a inside the vector, so the vector is created as you do that, or you can already store as 3 separate elements. I prefer this way. Yeah, because then I know X, Y, Z, and then I have access to them, and then it becomes very obvious what's going on here in this function. But you can do both ways. I prefer this way. So if you run the simulation, Oh wait, I have to, I'll comment this one. So here now you have a situation where you have 3 steppables, right? Well, actually 4, one for initial conditions and one for each one of these different kind of versions of convergent extension that you want. And they will be competing with each other. So this is a case that you where you have to choose which one you want to run. So in this case, I'll comment those, the intermediate and advanced, and run only the simple one, okay? So you have to do this choice. You see that the one thing that you have to do is you have to first import from this file and then tell the compile to actually run it, okay? We can actually simplify this, and you can, if you have the same example in your computer, you can do this already, which is instead of download each one of them at a time, you can actually download all of them using this command. And this means that you don't need to have this extra line here to import each one of them. So that simplifies your code a little bit. So you just import all the steppables, and then you choose which one you're going to run. Does that make sense? It just becomes simpler. So here I'm going to run the simple one. Let me save. Go back here. Play simulation. Okay, I got an error now. Okay. Okay. I had a typo there. So this is basically the, I'll make it bigger. And I'll change the color here. Okay. And now you can see that I'm trying to converge the tissue, right? So I also have this other version here. So this is basically what you did, and this is another version that I asked you to do as a homework. I don't know what if you did or not. And in the second one is basically the same thing, but this time I go over all the second order neighbors. So here I still have the delete links, the same thing, and the create links that define the maximum neighborhood. And here I have a function neighbor list and get the neighbors of the cell. So in this function get neighbors, I create a list of all my neighbors. I go over all the neighbors of that cell, and if that's a neighbor, not medium, I do the neighbor loop again to get the neighbors of the neighbors. So of course, in this case, before I do get the neighbors of the cell, and here I have to get the neighbors of the neighbor. So put neighbor here. And then I check if it's the second order neighbor is not a medium, if it's a neighbor, and if the neighbor ID is not in this list, then I put it on the list. And I put it as an ID, not as a cell. So this check here is to check if they are not duplicated the entries there. If the neighbors are right there, you don't put it back. After I complete the list, I shuffle it, and then I return, and then I get the list here. Okay. So if I could have put this right here, but then it's going to be indented. So it's better to separate your pieces of code into functions, which will look more cleaner. So after I get the neighbor, then I can actually get the distance between the neighbors, calculate the angle, and check if I want to make the link or not, and then I make the link. The other thing that you may notice that I don't go over all the neighbors that I create in my list. I only go from the first one to a certain number of neighbors. So instead of going for neighbor in neighbor list, stop here, I open and I slice from the first until up to the maximum number of neighbors of the cell. This means that I will not connect to all the possible neighbors, because now I'm going over second order neighbors, so I have more links to make, but I only do the first 3 ones, okay? And so each cell would only make 3 neighbors. And this actually works better, first because you're grabbing cells from outer side. So if I stop now and run this second steppable, you see the results will be better. You can already see that you have more links in the cells. However, okay, I made a mistake here. What was the mistake? Can you catch? So, from look at the simulation, what do you see? Every direction. Yes. Okay. So where I likely did the mistake? Where? Yeah, what did I choose? 90 degrees. So 90 degrees on this direction, plus or minus, 90 degrees to the direction, plus or minus. I'm pulling from everywhere. Not surprisingly, nothing works. Well, the tissue becomes compacted, right? But it doesn't work. So why don't you play with this link? Let's make this a very shallow angle, right? Let's stop and try again. Now I have very few links forming, mostly if the cells are already aligned. And well, they can make the links a little bit longer because they can reach up to the second neighborhood. But well, you see some convergent extension now, but it's not that great, right? You're basically making your tissue a little bit more stiff in one direction. So let's make now what I said before. Let's make pi over 4, 45 degrees. Stop, play again. Work? Makes sense? Okay. Any questions on this second one? I can also make the maximum number of neighbors to 1, and then of course this will not work very well. Actually, if I make the ones from 1 to, no, it's working. Sometimes the cell still can have 2 links because it's the link that the cell creates and the link that the neighbor created with the cell. So you still see some cells with 2 links because of that. Okay. If you want to make an absolute constraint, the cell can only have 1 or X links per time, then you have to, before make the link, you have to count how many links that cell has. That would be more code, more complicated, but so the idea is that you have one model, one idea how to implement it, but the actual implementation of the model can have many kind of variations and many flavors. And even the exact same model that I run in my computer, in your computers, that you code, everyone coded a little bit differently, right? So you have the conceptual model, the mathematical model, the computational model, and the actual implementation that you make. So as you go down from the idea to actual implementation, things start to branch more and more. Okay, so I will stop the simulation and show now the advanced one. Now, the idea behind the advanced is that in the previous models, all the cells were pulling in the same axis, the x-axis. And the idea is that maybe this, which implied that all the cells know and which direction they would pull, and they all agree to pull in the same direction, and they are perfectly aligned with each other in respect to the decision. But in reality, that maybe not what the cells are really doing. In reality, probably the cells have an internal vector or some kind of orientation, and then they pull according to this orientation. So, and if this information is stored locally by the cells and not come from an external kind of signaling, then we expect to have variations in this orientation, right? Or you can even expect that a part of the tissue have the cells oriented in one way, and other part of the tissue have cells oriented in a different way. So a good further modification of the model is to add a vector orientation to each one of those cells. And then when you go the loop, you don't compare the angle of the links with the x-axis, but you compare the angle of your link with the whatever orientation your cell has. So here, this means that at the beginning of simulation, you have to give the cells a vector, okay? And there's no property of the cells called vector. It's something that you have to create and add to CompCell. So here, what I did is, what CompCells allow us to do is associate a dictionary, an empty dictionary to all your cells, which is called cell.dict. And in this dictionary, you can specify any kind of key or entries, and then you can store anything that you want in this dictionary. And the advantage of that is that this dictionary is not only available for all the functions that are steppable, but also available across steppables. It's something that can be retrieved and modified from any place in the code. So to do this dictionary, is already done here, but I can show how to do. Let's say for cell and self-cell list, and you want to store something in a dictionary of that cell, you can go here, CompCell 3D Python, cell attributes, and access modify dictionary attribute. You click here, and it creates some attribute name, which can be whatever you want. And here you can store an object which can be whatever you want. It can be a string, it can be a scalar, or it can be another dictionary with other entries inside, or it can be a list as I did here. So here in this list, it's an entry with two numbers. The first one will be X, the other one will be Y. And then here I create a second dictionary would be the angle that you can translate this in terms of the X, Y axis of your simulation. So here I'm still giving all the cells the same angle, okay? But I can make a random number here if I wish. Okay. So after I do this, I go to step function, delete and create links. The delete links are the same thing as before. The create links is almost the same thing as you had before. The only difference is that after I get the angle that I'll calculate will be the difference between the angle that I get from my original axis from 8 and 2 minus this angle that I get for that particular cell. So look at the difference, and then I do a module operation with pi to make sure that this difference will be between minus pi and pi. Okay. And after I do this thing, then I'll, instead of comparing my angle with the x-axis, I'll be comparing my angle with this other axis defined by this vector angle. And then I make the link. Everything else is exactly the same as before. So if I run this version of the code, what do I have to do? Remember? First, I have to turn off the later one and then activate this steppable. So I have to go back here. I turn off this one, comment, and then I turn on this one. All right, save. And now I go here and I can play this simulation. So after 200 steps, now you can see it's the same thing as before, but now my angle was changed from, whoops. I changed my angle here. Instead of being the oriented one way, you'll be oriented 90 degrees from it. I can also make this 45 degrees in an angle, and then I can stop, run simulation again, and now everything should be in the diagonal, right? Yeah, still vector, but because this vector is a property of the single cell, I can play around and make every cell to be have a slightly different vector, right? Right now it's the same, but I can come here and do something like, well, if cell center of mass is bigger than so x direction up or down, the middle one, I can give it a different vector. I can give a minus and then it should be the other direction. Can you guess what the shape of the thing will be? Ah, I'm missing a C. What? An X shape? Okay. Okay. So it will be an X. Other. Okay, let's run and see. Okay. The actual shape will be an inverted V in this case. Well, right now it looks like the shape of the face of a cat, but on the other side, right? Then I think this part here will look like a, I don't know how to move. Now it looks more like a wolf, but inverted. But eventually you'll make the V as you predicted. And then now you can do your own variations and add noise on each one of those cells and get the very different shapes. Okay. So the files are there for you to play with. Maybe I'll upload this new version because there was a typo there somewhere, but you're free to play and try to make your own shapes or test how robust is this process to variations small variations or big variations into the relative orientation of the cells. And a nicer thing you do too is to maybe add some kind of gradient of some chemical and make the cells read this gradient and decide to which direction they point to, right? Or add the PCP signaling between the cells, make them orient some way, and then having the extender Filippo activity according to this orientation that they have. So these are all things that you can play. What? The Star Trek? Okay, with this I end the Convergent extension exercise. And now, because you're still in the topics of links and make links between cells, and I gave on the board example of making a cell with links that are internal or external, maybe we can actually do this exercise and have links between internal compartments of cells in the context of an epithelium. So we stop it here, but maybe we can also do this kind of example. Wow. Which will maybe create an epithelium with basal, core, and apical sides, and add, and in this case, we only have links between the compartments. So if I have the whiteboard, and then you can play with these links to make the cells more elongated or less elongated. Juliano? We have here. So this would be, the example we had, I showed here on the board yesterday. Maybe we are just a good idea. We define lots of cells. We define a basal side of the cells. An apical side of the cells. And well, a core part of the cell, and then we specify links between those compartments. And if we increase this link, the target length, we can make the cells to elongate or to shrink, so you can control the aspect ratio of the cells. Right? And then on top of that, you can also add links between the neighboring apical compartments and shrink them over time, which should cause the cells to be edge-shaped. And of course, if you add this to all the cells, nothing really happens. But if you just add a bunch of cells in the center, then what you have is you start to get some kind of apical constriction. So here you'll not see the leaks, but I'm just making those cells here to have decrease the apical constriction, the target length, or the spring constant between them, and that will create some kind of furrow between them. Right. So my idea is, why don't we try to create this geometry in CompCell, and then you learn how to not only play with the links which are internal versus the links which are external to your code, but we will also learn how to actually create cell compartments, how to create cells that have multiple compartments in simulation, which will be used later by Gilberto for his cell crawling demo. Make sense? Have a question? Okay. So let's go to tweet it and create a new file. I'll close this. So Convergent to Python, new project. And let's call this epithelium. Here, I would suggest extending your X direction further. Just make. Now, well, there's no really need to make the. Let's make the Y 128 because we want to have to save a little bit of space in the Y direction. No, it's just that then you have 1, 0, 0, 0, 0. Not sure how much faster it makes. But.
Oh, so the simulation is always
No, it's just when you redesign the for 4.0, I suggest increase the size of the lattice. And then James says, well, if you're going to increase to 200, make it 256, which makes sense. And let's add periodic boundary on X. So your cells wrap around on the X direction. And choose rectangular slab. Yes, okay. Continue. Now the cell types. Now, here in this simulation, we are not really dealing with cell types. We are dealing of cellular subdomain types, right? So we have to basically do the basal, the core, and the apical side of the cell. So that would be our cell type. So we can write here core, add, basal, add, apical, and add, okay? However, you also need something else. So for now, we have 4 domain types, the medium, right? The core, the apical, the basal. But maybe you also need some extra one, because the way you're going to initialize the cells is not drawing them as it is. It's really a domain or generalized cell. I prefer the word domain. What it happens is that the way the strategy to generate those cells will be the following. We will create first a cell of type core, and then we add some pixels inside to be the basal ones, and add some other pixels inside which will be the apical ones, randomly inside its volume, and then let they sort out by themselves according to the adhesion preferences. But for this strategy to work, this upper part here can have different properties than the lower part of the cell. So on one side, I want to be medium. The other side, I want to be something else. Okay. So maybe, for this natural sorting to occur, oops. What I want is that this side, the cells on the bottom side face either the medium or something else, and the upper part of the cells face something else that's not medium or something else. So maybe we can create something called an upper cell here. That spans the whole thing, which may be called the ECM. Okay, and then we draw the ECM on top of it. So let's make the fifth cell type to be the ECM. And add. Continue, no chemical. So it's what I did. Okay, all the cell types: medium, core, basal, apical, and ECM. Is everybody following? Okay. You can freeze ECM. Let's do it. Yes, that's a problem. Then you cannot. Later on, you cannot really do the invagination. That's a bit the problem. So let's not freeze ECM. Okay. Continue. Chemical fields. Well, we can also unfreeze later. But, continue, and now we need contact. Because now we have compartments, we need internal contact between the compartments. So I have contact and internal contact. We need volume local flex, cell neighbors, and focal point plasticity. Okay, these are all the things we need. Why we don't use compartments? Well, I'll say that I never uses this option. Maciek, can you expand on this? What would be the compartments option here?
So with the compartment option, this is old style of grouping those two together. So essentially, it's somewhat less flexible, actually. So first implementation of compartmental contact plugin was that we actually created a plugin that where you specified in one plugin external and internal stuff. So it's, I think this one is more convenient than the way Julia showed. So.
Okay, so select, thanks Maciek. Select contact internal, focal point plasticity, volume local flex, center of mass, and cell neighbors. Okay, got it? So let's continue. Done. This is our simulation. And here is everything that's in it. Now, first you have lots of, on the focal point plasticity plugin, you have, it automatically makes all the possible combinations of everything, right? But let's first turn everything off. Let's make all the internal and external things. Can comment everything. And let's at first not use links. Let's just try to make the right shape of the cells. Let's just make the compartment cells. Okay. Line. So line 87 to 245. Actually, everything that has the ECM on it, we can comment already because you not make any links with the ECM. Or you leave that if you want to do and explore what will happen. So select everything and hit the, in Mac it's going to be Command D, and in Windows is something else that you have to hit. I think it's, well, you have to go edit and block comment, right, to block everything.
So we're starting with, yeah, I'm sorry, contact internal.
Yes. Yeah, that we keep. You keep that. You need. You're basically keeping a comment everything. Yeah, you can comment the whole stuff. Yes. And the uniform initializer, let's use this to make a first line of cells of type core that spans the x-axis in your simulation. So how you do this? First, you want your x to go from 0 to 256. You're right about the middle. Remember, y is just 128, so the middle be, and let's make your cells, they have to be 8 by 8 to actually tile the whole thing though, because it's 250, so it has to be powers of 2. So let's make the width of the cell 8, and then 64 plus 8. And on the types here, we just make the core type. Okay. So what you're doing here, we have our space, which comes from 0 to 56, and then from 0 to 128. And you're creating a single line of cells using the uniform initializer that goes like this. And each cell will be a square of size 8 by 8. And the reason I choose 8 is because 8 will actually you have the same, an integer number of cells result of a cell being kind of halfway here. And here I choose 64 to 72 because I want this to be 8 pixels. Make sense? So if you run this, and if you didn't make any kind of mistake that I cannot see now, you should get your initial line of cells. Just check that in your computer. Did it work? So let me try this. Just hit this step function once, and then, okay, it worked for me. Hopefully it worked for you guys as well. I just want to turn on the cell borders, and there it is. Do you all got this? Okay. No? Okay. You didn't? Yes, because you have periodic bound conditions on X. Yes, they do have. Because when you click here, it already went one Monte Carlo step, even though it does not say it here. So there is a bug in the player that is not is in configuration after one Monte Carlo step, but does not show here. So there's a bug here, which it's kind of hard to fix, given the way that matching inherit comp cell. But ideally, you click this once and not do anything. It will be wheel time 0, so you can actually see exactly what you put in your initial configuration. Yes. So now you create those cells. What you want to do now is add all the same on either the top or the bottom. Okay. And actually, if you just run the simulation, you see that all the cells will disappear because they don't have target volume, right? So let's now go to the steppable and fix this. So which function you have to do this fix? The start one, right? Because we want to do right at the beginning. So right at the beginning, maybe what you want to do is make a loop over all the cells, visit, maybe all cells of a given type, and the type will be core with capitalized. Even if you do with lower case, you have to here do uppercase, and then let's assign a target volume to be 8 by 8, so it would be 64, and a lambda volume, so to be 2, okay? And if you do this and run simulation again, now the cells will not disappear, okay? So the other thing that you want to do now is add the ECM on either the top or the bottom. And instead of using the uniform initializer, let's do this by hand from the Python level. So in the uniform initializer, we can make another line from, let's say, X from 0 to 56 and Y from 0 to 64 and add the ECM here. But what that you create is going to create lots of ECM cells. And maybe you want to just have one single one that spans at the whole top or the whole bottom. Okay? And the problem with the uniform initializer is that you can only make square. You cannot make rectangles, and you cannot make spheres. You cannot have this flexibility in shape. But from the Python level, you can specify this pixel, this pixel, this pixel, this pixel, this pixel will be of this cell type. Okay. So have you seen this before? No? So now let's do it. So here, go, after you assign, or either before or after, you assign the volumes of the cells. Let's create ECM. It's always a good idea to comment what you're doing. So set target, set properties. No, because I want to have ECM on top and mid on bottom. Because the apical cells that the epithelium cells that we make, I want the basal site to be touching as ECM and the apical site to be a different cell type, which let's call it the medium. Yes. You see how it can be done. You see. So create ACM. So here compensatory deploy to have cell manipulation. And one of the options is create a cell. So let's choose that, create cell. Create cell. Cell manipulation. There's create cell detailed. Let's do create cell detail, which is better. Choose create cell detail. Well, we have to fix the indentation. So here creates a position, a Y position, a size, and this what interests us. It creates a cell, and this second one says exactly where the cell will be in space. So we don't need those first three, we can delete them. And this cell watch will be the ECM cell, so let's create ECM is going to be self.new cell type ECM. Okay.